Tonight, at some point, you will probably walk into a room and forget for just a heartbeat why you came. Or you will feel a cold prickle at the back of your neck in a quiet house and be certain, for 1 second, that you are not alone. We explain these small moments away as tired nerves, a draft, a trick of a busy mind, and most of the time we're right to. But stay with a stranger possibility for a little while. What if a few of those moments are the faint outer edge of something enormous? Something that has nothing to do with your brain and everything to do with the shape of the reality you happen to be standing in. Because when we finally measured the outer boundary of the universe, we did not find a smooth sealed sphere. We found what looks like a wound older than the first star that ever burned, with something quietly leaking through it. So here is the question I promised to answer before this night is over. Is our universe a sealed box? Or is another reality pressing in from the other side, close enough to touch? Get comfortable and let your shoulders come down. Subscribe if you have not, and stay with me, because the trail we're about to follow runs all the way from a scar in the oldest light there is to the single millimeter of space in front of your face. Let's get into it. Part 1. The Forgotten Room. Have you ever walked into a room and completely forgotten why you went there? You stand in the doorway, hand still resting on the frame, and the reason that carried you across the house a moment ago is simply gone, as if someone reached in and lifted it out of you. Or maybe you have felt the other thing, the sudden chill that has no source, the prickle at the back of the neck that arrives when you are alone in a quiet room, the certainty, for just a second, that you're being watched. We have comfortable explanations for all of this. We say the brain is tired. We say it is a trick of memory, a misfiring of tired neurons, a draft from a window we forgot was open. And most of the time, those explanations are almost certainly correct. But I want you to sit with a different possibility tonight, not because I can prove it, but because when I started following the physics all the way down, I found myself unable to fully let it go. The possibility is this. What if some of those small, strange moments are not entirely inside your head? What if they are the faintest edge of something much larger? Something that has to do not with your brain at all, but with the shape of the universe you happen to be standing in. Because here is what changed my view of the world. For most of human history, we assumed our universe was a closed and solid thing, a sealed room with everything we would ever need already inside it. Safe, isolated, complete. And then we began, very carefully, to map its outer boundaries, to measure the oldest light that exists and read the shape of the cosmos off of it. And what we found was not a smooth, sealed sphere. We found damage. We found what can only be described as a dent, a scar, a place where the fabric of reality looks as though something from outside physically struck it and left a mark that has never healed. An energy, it seems, has been quietly leaking out through that wound ever since. The equations that describe our cosmos do not show a universe floating alone in a calm and empty void. They describe a universe that may be pressed up against a crowded ocean, jostled and shouldered by enormous objects that could be sitting just a few centimeters away from you right now, in a direction your body cannot point toward and your eyes were never built to see. That is not a poem. For a small number of very serious physicists, that is a reading of real data. So tonight we're not just going to talk about distant stars and galaxies, though we will get there. We're going to walk, one careful step at a time, through the actual evidence that the wall between our reality and whatever lies outside it may be thinner than anyone wanted to believe. We're going to look at a cold bruise in the sky older than the first star. We're going to follow a current that appears to be dragging a tenth of everything we can see towards something we cannot. We're going to fold up a fifth dimension and hold it in our hands. And yes, by the end, we're going to ask the most unsettling question of all, which is what actually happens to your body, to your atoms, to the very idea of you, if that wall ever truly breaks. I want to be honest with you before we take a single step further, because that honesty is the whole point of this channel. Some of what we cover tonight is rock solid, measured to dizzying precision, confirmed by satellites and by physics that runs the machine you are listening on. Some of it is genuinely unexplained, real open mysteries that keep working scientists awake. And some of it is speculation, careful and serious speculation by real physicists, but speculation all the same, ideas the mainstream does not accept, and in some cases has actively pushed back against. I will tell you, every single time, which is which. I am not here to frighten you into believing something. I'm here to walk you right up to the edge of what we know and let you feel, for a couple of hours, how strange and thin that edge actually is. So get comfortable. Let your shoulders drop. If your eyes are closed, keep them closed, because none of this requires you to look at anything except the pictures your own mind is about to build. We are going to start with the one assumption that everything else in physics quietly leans on, the assumption that the universe is smooth and even and the same in every direction. Because it was in the moment we finally tested that assumption in the most precise way we ever have that the first crack appeared. Let us begin at the beginning, with the light left over from the birth of everything. Part 2. The universe that was supposed to be smooth. To understand why the map we made was so disturbing, you first have to understand what we expected the map to look like. And to understand that, we have to talk about a single word that holds up almost the entire building of modern physics. That word is isotropy. Isotropy means sameness in every direction. It is the quiet assumption underneath the standard model of cosmology, the rules that ultimately dictate how the atoms in your body hold together tonight. The assumption goes like this. The Big Bang was, as far as we can tell, a nearly perfect and symmetrical event. It did not explode outward more forcefully in one direction than another. It did not favour north over south, or left over right. And so, if you look out at the universe on a large enough scale, in any direction you choose, the temperature and the spread of matter should come back the same. No special directions. No preferred axis. No lumps. Imagine pouring a single drop of milk into a cup of hot coffee and then stirring it, slowly and patiently, for a very long time. At first there are swirls and streaks, pale ribbons folding through the dark. But if you keep stirring, eventually the whole cup becomes one uniform shade of brown. There are no lumps left, no bright threads, no dark corners. Everything is evenly mixed. That, according to the standard model, is what the early universe should look like when you smooth it out. A calm, featureless soup of radiation with no scars and no secrets, the same wherever you dip your spoon. I want to give you a feel for how extraordinary the measurement really is, because the numbers do not land unless you slow down with them. When we say the ancient light is uniform to about 1 part in 100,000, here is what that means. Take the average temperature of the cosmic background, and then look for the tiny deviations from it, the places that are a hair warmer or a hair cooler. Those deviations are so small that if you shrank the entire observable universe down to the size of a calm mountain lake at dawn, the ripples on its surface would be smaller than the thickness of a single human hair. This was not measured all at once. In the early 2000s, NASA's earlier satellite, called WMAP, made the first fine map and hinted at the anomalies. Then Planck came a decade later with sharper eyes and confirmed them. 2 different spacecraft, 2 different teams, 2 different generations of technology, both looking at the same ancient light and both seeing the same faint, stubborn strangeness in it. When 2 independent instruments agree on something odd, physicists stop being able to wave it away as a quirk of one machine. Let yourself rest in that image for just a moment before we go on, because it is genuinely lovely, and this is the kind of night to let a lovely thing sit. Somewhere above you, right now, in every direction you could point, there is a faint glow of ancient warmth left over from the birth of everything, arriving after nearly 14 billion years of travel, cooled almost all the way down to the coldest temperature there is. It is the same in the direction of your ceiling as it is toward the floor, the same over the horizon at dawn as at midnight. It surrounds you like the inside of an enormous softly lit sphere, and it is only when you measure it with almost impossible care that the sphere reveals it is very slightly the wrong shape. For decades this was not just a hope, it was the foundation. Every equation we use to calculate the age of the universe, its size, its expansion, its ultimate fate, sits on top of the assumption that the cosmos is fundamentally smooth and the same everywhere. If that assumption cracks, a great deal of what we think we know begins to wobble along with it. So it mattered enormously that we test it. Not with philosophy, but with an instrument. In 2009, the European Space Agency launched a satellite called Planck, named after Max Planck, the father of quantum theory. Its job was almost absurdly delicate. It was built to measure the cosmic microwave background, the oldest light in all of existence. Let me tell you what that light actually is, because it is one of the most beautiful facts we have. For the first few 100,000 years after the Big Bang, the universe was so hot and so dense that it was opaque, a glowing fog in which light could not travel freely. Then, roughly 380,000 years in, the universe cooled just enough for that fog to clear, and the light that had been trapped inside it was suddenly released, free to travel in every direction. That light has been travelling ever since, for nearly 14 billion years, stretched and cooled by the expansion of space, until today it glows faintly at microwave wavelengths, only a few degrees above absolute zero. When you point an instrument like Planck at the empty sky, you're looking at a photograph of the universe as an infant. You're seeing the very first thing that could ever be seen. By 2013, Planck had sent back the most detailed map of that ancient light that human beings had ever made, and in most respects, it was a triumph for the standard model. The universe really is smooth, to about 1 part in 100,000, which is astonishingly uniform. If you scaled the whole cosmos down to the size of a calm lake, the ripples would be smaller than the width of a hair, so in a sense the milk really did mix into the coffee. But the map was not perfect, and the imperfections were not random static. They were structured, and they were strange, and some of them had already whispered to us years earlier in the data from an older NASA satellite called WMAP. Planck did not make these anomalies go away. It sharpened them. The first strange thing was this. When you divide the sky into 2 halves, the 2 halves do not match. One hemisphere of the sky is slightly more structured, slightly more textured than the other. Physicists call it the hemispheric power asymmetry, and it is exactly the kind of thing that should not exist if the universe is truly the same in every direction. It is a small effect, only a few %, but it is there, and it is coherent. Then there was a second oddity, an alignment of the very largest temperature features across the sky, features that seemed to line up along a single preferred direction. The alignment was so unexpected, so contrary to the promise of a directionless universe, that astronomers gave it a name that tells you exactly how they felt about it. They called it the axis of evil. Now, I have to be careful and fair here, because this is where honesty matters. Many physicists believe these large-scale anomalies could be statistical flukes, rare but allowed patterns that show up occasionally in a random universe, the way a fairly shuffled deck will sometimes hand you a suspicious run of cards. Others suspect leftover contamination in the data, foreground signals from our own galaxy that were not perfectly scrubbed away. The debate is genuinely unresolved. Nobody can say for certain that these anomalies are new physics, but nobody has been able to make them fully disappear either. They have survived 2 different satellites, 2 different teams, 2 different decades of scrutiny. And here is what I want you to feel, sitting right there where you are. You're not floating inside a perfect balanced sphere after all. The oldest light in the universe, the first photograph ever taken, is lopsided. The structure you live inside is, in some subtle and stubborn way, bent. And once you accept that the whole thing might be tilted, the natural next question is the one that changes everything. If the universe is not perfectly smooth, then somewhere in that ancient light there might be a single place where the imperfection is not subtle at all, a place where the map does not just lean, a place where it breaks, and when astronomers went looking for the worst of it, they found exactly that. They found a wound. Part 3. The Bruise and the Missing Galaxies. Inside that colder, stranger hemisphere, the Planck telescope found something that has bothered cosmologists for years. It is a single region of the sky, sitting in the direction of the constellation Eridanus, the river, that is noticeably colder than everything around it. Not by much in absolute terms, only about 70 millionths of a degree below the average temperature of the background. But it is spread across a patch of sky roughly 5 degrees wide, which is about 10 times the width of the full moon, and a cold region that large and that deep is not what the smooth standard universe comfortably predicts. Astronomers call it the cold spot. I think of it as a bruise on the oldest skin there is. Now, why should a cold spot be so troubling? To answer that, you have to remember one of the most reliable rules we know, the second law of thermodynamics. Heat flows from hot to cold, always, until everything reaches the same temperature. Drop an ice cube into warm water, and the two will meet somewhere in the middle. The universe has had nearly 14 billion years to even itself out, to let heat flow from its warmer regions into its colder ones until the difference smooths away. And yet this cold region has not healed. It has sat there, stubbornly colder than its surroundings since almost the very beginning of time. Something, it seems, has been holding it open. For a while, that was the whole mystery. a cold place that would not warm up. But then astronomers did the obvious thing. They pointed their instruments at the exact centre of the anomaly and asked a simple question. What is there? A cold spot in the sky is often just the fingerprint of some enormous dense object between us and the ancient light, something so massive it drains a little energy from the photons passing by. So they expected to find a giant supercluster, a wall of galaxies, a dense cloud of gas, something heavy enough to explain the chill. What they found instead was the opposite of an object. They found an absence. In 2015, a team led by the astronomer Istvan Sapudi announced the discovery of what they called the Eridanus supervoid. It is an enormous continuous region of near emptiness, and its scale is difficult to hold in the mind. It stretches roughly 1.8 billion light-years across. To give that number some meaning, it is among the largest single structures ever identified in the entire history of astronomy. But unlike a great wall of galaxies or a bright supercluster, this structure is not defined by what is in it. It is defined, almost entirely, by what is not. According to the standard picture of the cosmos, matter should be spread out fairly evenly, like butter across bread. A region of space this enormous should be humming with energy. It should hold something on the order of 10,000 galaxies, along with gas clouds and dark matter and the combined light of trillions of stars. But when we look into the Eridanus supervoid, the lights are turned down low. The matter is not merely dim. A great deal of it is simply not there. The void is underdense compared to the rest of the universe, missing a significant fraction of the material it ought to contain. Picture walking through a dense, noisy city at rush hour, the buildings pressing close, the sound of traffic and voices everywhere. And then imagine stepping around a corner into a single enormous block where the buildings, the people, the cars and all the sound have simply vanished, leaving only cold, empty pavement stretching farther than you can see. That is the feeling of this void. And because there is so little matter inside it to radiate warmth, and because of a subtle effect where the light passing through a stretching, emptying region loses a little of its energy on the way, the void chills the ancient light that crosses it. That is the mainstream explanation for at least part of the cold spot, and it is a good one, a great emptiness, cooling the oldest light. Let me unpack the mechanism a little more, because it is subtle and beautiful, and it shows how careful the ordinary explanation actually is. In a universe that is simply expanding at a steady rate, a photon that falls into a dip in gravity, like the gravitational well around a region of matter, climbs back out the other side with exactly the energy it started with. What goes down comes back up. But our universe is not expanding steadily. Because of dark energy, the expansion is accelerating, and that changes the accounting. When a photon crosses a huge void during an accelerating expansion, the void actually flattens and stretches a little while the photon is still inside it. So the photon climbs out of a shallower dip than the one it fell into, and it loses a small amount of energy in the process. Lose energy, and light grows a little colder. Multiply that tiny effect across a void 1.8 billion light-years wide, and you begin to chill the ancient light in a way we can actually measure. That is the honest, elegant, mainstream story, and it requires no other universe at all. It is worth admiring on its own terms. Take a slow breath here, because I want you to picture the scale one more time before we sharpen the mystery, and scale is something the mind can only approach gently. Light, the fastest thing there is, crosses the distance from the Sun to the Earth in about 8 minutes. It crosses our entire galaxy, edge to edge, in about 100,000 years. And this single empty region, this one quiet hole in the sky, is so wide that light would need well over 1 billion years just to cross from one side of it to the other. If you set out tonight at the speed of a light and flew straight into its heart, generation after generation of everyone you have ever known would live and die, and civilizations would rise and fall on Earth, and you would still be falling through the emptiness, the last few galaxies thinning out behind you, the darkness ahead deepening, with no far shore yet in sight. But here I owe you the honest footnote, because it matters. The void is real, and it is genuinely gigantic. But whether it is empty enough and large enough to fully explain the depth of the cold spot is still debated among cosmologists. Some argue the numbers do not quite add up, that the void can account for some of the chill but not all of it, leaving a stubborn remainder that still has no agreed explanation. I have also seen the void described as 30% empty in some tellings, And I want to be straight with you. The honest figure the surveys support is more like 10 to 20% under dense. The drama is real. The exact number is smaller than the scariest version. Both of those things can be true at once, and yet even at the honest figure, there is a genuinely strange physical problem lurking here, and it is worth sitting with. Gravity is how you clear out a region of space. Matter pulls on matter, and over time it drifts together into clumps, leaving thinner regions behind. But gravity is slow, and it works over enormous distances only very gradually. To carve out a hole 1.8 billion light-years wide, to gently push the equivalent of thousands of galaxies worth of material out of the way by gravity alone, would take an immense amount of time. By some estimates, longer than the current age of the universe. Which raises a quiet, uncomfortable question. If gravity as we understand it is not quite fast enough or strong enough to have dug a hole this size in the time available, then how did the hole get dug? There are careful, ordinary answers to that. Voids do form naturally. The universe is a foam of them, and rare large ones are allowed. But this is the exact seam where the speculative story slips its fingers in. Because if you are already inclined to wonder whether our universe is a sealed box or a membrane pressed against something else, then a region of space where thousands of galaxies seem to have been scooped out of existence starts to look less like a random quiet corner and more like a footprint. Like the place where something leaned on the fabric of reality and pushed. I want to be clear that I am not asking you to believe that yet. I am asking you to notice how the question feels. Because if something powerful enough to empty 1 billion light-years of space is out there, and if it did its work before the first star ever ignited, then the natural next thing you want to know is whether we are safe. Whether the thing that made the wound is finished, or whether it is still out there, still leaning. And the first step toward answering that is not a telescope at all. It is a calculator. Because before you decide something impossible has happened, you have to ask how unlikely it really was. Let us put a number on the wound. Part 4. The dice someone turned over. Whenever something looks impossible, a good scientist does not immediately reach for the extraordinary explanation. The first, most disciplined question is always the boring one. Could this just be chance? The universe is immense, and sprawling things throw up strange coincidences all the time. Maybe the galaxies simply failed to form in that patch of sky by bad luck. Maybe the cold region is just an unlucky roll of the cosmic dice. So physicists did the responsible thing. They tried to calculate the odds. When researchers ran the numbers on the cold spot, asking how likely it is that a region this large and this cold would appear purely by chance in a smooth, standard universe, the answer that often comes back is somewhere in the range of 1 to 2%. The figure you sometimes hear quoted is 1.85%. Now, I want to be fair about what that number means, because it can be made to sound scarier than it is. 1 in 50 or so is unlikely, but it is not miraculous. Unlikely things happen constantly, precisely because there are so many opportunities for them to happen. And there is a subtle trap here that honest scientists point out. We noticed the cold spot because it was unusual. When you go hunting through a huge sky specifically for the weirdest feature in it, you are almost guaranteed to find something that looks improbable, in the same way that someone will always win the lottery, even though any particular ticket almost never does. So I am not going to tell you the odds prove anything. They do not. But I will tell you why, to the people who suspect something outside is involved. That small number feels like a red flag rather than a shrug. It comes down to what kind of box you think you live in. If the universe is a truly closed system, a sealed container where nothing gets in and nothing gets out, then energy is conserved. It cannot simply vanish. Every bit of heat and matter has to be accounted for somewhere. And in that closed box, a cold, empty region this extreme is a genuine statistical strain on the model. Not impossible, but awkward. The kind of awkward that makes a physicist tug at their collar. Let me make that strangeness physical, because a number on a page never lands the way an image does. I want you to think about the room you're in right now. The air around you is not still. It is a storm of molecules, trillions upon trillions of them, moving in every direction at hundreds of miles per hour, colliding and rebounding billions of times each second. It feels like calm, quiet air because all of that motion averages out. The molecules are spread evenly through the room, pressing on you gently and equally from all sides. Now here is a fact that is true, and that almost nobody ever thinks about. There is nothing in the laws of physics that strictly forbids all of those molecules from happening, purely by chance, to rush into one corner of the room at the same instant. It is allowed. Every molecule is moving randomly, and it is conceivable that in one moment they all randomly move the same way, leaving the rest of the room, and you inside it, in a sudden hard vacuum. The air simply gone, your ears popping, your lungs finding nothing to breathe. It is not against the rules. You have never once worried about this, and you are right not to, because the probability is so unimaginably small that you can bet your entire life against it and win, every second, forever. The universe would run for a number of ages far longer than its current age before you would expect to see it happen, even once in a single room. That, more or less, is the intuition behind why a closed universe should not casually produce a cold, empty scar the size of the Eridanus supervoid. In a sealed box, the deck is stacked so heavily against it that when you see it anyway, a quiet voice starts to ask whether the box is really sealed at all. There is a discipline that good physicists practice here, and I admire it enough that I want to describe it to you, because it is the opposite of how a conspiracy thinks. When a scientist notices something unusual, the first thing they do is try to talk themselves out of it. They ask whether the instrument had a flaw. They ask whether the way they analysed the data quietly nudged the result. They ask whether, given how many patches of sky they searched, an oddity this strong was actually likely to turn up somewhere just by chance. This last one has a name, the look elsewhere effect, and it is the single most important guard against fooling yourself. If you scan 1,000 different regions of the sky looking for the strangest one, then finding a 1 in 50 oddity is not surprising at all. It is nearly guaranteed. So the honest scientist deflates their own excitement on purpose, subtracting the drama until only the residue that survives every objection remains. The cold spot has survived a fair amount of that deflation, which is why it is still discussed. But it has not survived all of it, which is why most cosmologists file it under unusual rather than under impossible. I point this out because it is the exact spirit I want us to keep for the rest of the night. It is easy, and frankly it is fun, to let each new anomaly stack on top of the last until the tower feels overwhelming. But the honest move is to keep asking, at every level, could this just be the ordinary universe seen from a dramatic angle? Sometimes the answer is yes, it probably is. And sometimes, in a few genuine cases, the answer is that nobody can quite make the oddity go away, and those are the cases worth staying up for. The trick is never losing track of which is which, even when the story is pulling hard in one direction. And that is the forbidden thought the low probability pushes you toward. Not that the dice rolled badly, but that the system is not closed, that the heat and matter missing from that region did not vanish by chance but went somewhere, drawn out through some opening we cannot see. The dice, in this reading, did not simply come up with an unlucky number. Someone reached onto the table and turned them over. The anomaly was not formed by internal bad luck. It was formed by external pressure. The void is not a random clearing in the forest. It is where something reached in from outside the forest and pressed down. I want to hold us both back for a moment right here, because this is the exact point where a documentary can quietly lie to you by getting excited. Nothing we have said so far proves an outside anything. Everything we have covered, the anomalies, the void, the odds, has a respectable mainstream explanation that requires no other universe at all. Rare flukes are allowed. Great voids do form. The honest state of things is that the cold spot is unusual and not fully explained, and that reasonable physicists disagree about how much of a mystery it really is. Keep that in your pocket. Hold on to it. But also notice what just happened inside you, if you were following closely. The idea got in. The image of a hand reaching onto the table, turning the dice, is hard to put back down once you have picked it up. And it turns out that image is not something I invented to unsettle you. Years before the cold spot was ever measured, before the Planck satellite had even been built, a physicist wrote down in equations that a hand exactly like this one should have left a mark exactly here. She predicted the wound before we found it, and when we finally looked, it was waiting for us, at the right place, the right size, and the right temperature. That is where we go next, and it is, for my money, the single strangest turn in this entire story. Part 5. The Woman Who Predicted the Scar. To understand why this next part matters so much, you have to understand the problem it solved, and the problem was reputation. For decades, string theory was mocked, even by physicists who admired it, as philosophical math. It was beautiful, it was intricate, and it seemed impossible to test, which in science is close to a fatal flaw. The theory suggests that the smallest constituents of reality are not point particles, but tiny vibrating strings, and that these strings can only vibrate consistently in 10 or 11 dimensions rather than the familiar 4. And buried inside the mathematics was a number that sounds like a joke but is not. The theory implies there could be something like 10 to the power of 500 different ways to fold up those extra dimensions, each fold producing a universe with slightly different laws of physics. 10 to the 500, a 1 followed by 500 zeros, more possible universes than there are atoms in ours by an incomprehensible margin. Most physicists treated this boundless catalogue, this landscape of possible universes, as a purely mathematical abstraction, a list of what could be, written on a chalkboard, with no claim that any of the other entries were physically real. It was a curiosity, and to some, an embarrassment. But in the mid-2000s, a theoretical physicist named Laura Massini-Houghton, working with collaborators, proposed taking the landscape literally. She argued that this huge collection of possible universes was not just a list. It was a real place. Our universe, in her picture, was one bubble that had emerged from a high-energy background, the way a single bubble of steam rises and forms in a pot of boiling water. And if you take that image seriously, a consequence follows almost immediately. Bubbles in a pot are not alone. They crowd each other. They press against their neighbours, and sometimes, inevitably, they collide. This was not merely a pretty metaphor. She and her collaborators worked through the mathematics of what would actually happen if our young bubble universe had brushed against another bubble in the earliest moments of its expansion. And the equation said something specific. Such a collision would leave a bruise. It would push matter away from the point of contact and carve out a region that was colder and emptier than its surroundings. And crucially, because this was real physics and not just storytelling, the model made a prediction that could be checked. It said that if this picture of a colliding multiverse were true, then a future map of the cosmic microwave background should reveal a giant void, a cold spot, in a particular region of the sky. She and her collaborators even estimated roughly how large it should be, and which hemisphere it should sit in. This prediction was published before the Planck satellite returned its detailed results. The claim was on the record, testable and specific, waiting for the data to either confirm it or kill it. And that is exactly what a good scientific prediction is supposed to be. Falsifiable. A bet placed before the cards are turned over. Then, in 2013, the cards were turned over. The Planck data arrived, and the cold spot was sitting there in the southern region of the sky, roughly where her equations had said it should be, roughly the size they had suggested. For the people who had followed her work, it was a stunning moment. A guess about the structure of the entire cosmos, made years in advance from an argument about colliding universes, appeared to have come true. I want you to sit inside that moment for a second, because this is the emotional centre of the whole story, and it deserves to be felt rather than rushed past. Imagine being a person who wrote down, on paper, using nothing but mathematics, that there should be a specific kind of scar in a specific corner of the sky, born from a collision between our universe and another one, at a time before there were stars or planets, or eyes to witness it. And then imagine a satellite, built by hundreds of people over many years, quietly returning its map, and there, in the data, is your scar. In the right place, the right size, the right temperature, the vertigo of that, the sense of having reached out with pure thought and touched the actual architecture of reality, is almost too much to hold. It is the feeling of a prophecy coming true, except the prophecy was written in the language of gravity and quantum fields, and the thing it foretold was a wound in the fabric of everything. For those who believe her, this turned the cold spot from a random mystery into something else entirely. Not just an anomaly, but a signature. The first observational hint, they argued, that the multiverse is real, and that we live in a universe that has physically collided with another one. In this reading, we are not merely looking at a hole in the sky. We are looking at a verified crash site, the place where two realities touched. And now I have to do the hardest thing a storyteller can do, which is to pull you gently back from the ledge just as the view is at its most extraordinary. Because I promised you honesty, and honesty requires it. Laura Massini-Houghton's prediction is real, and it is genuinely remarkable. But it is not accepted by mainstream cosmology. Many physicists regard the match between her prediction and the cold spot as far less clean than the dramatic version suggests, and they point out that the cold spot has that ordinary explanation waiting in the wings, the great void chilling the ancient light, no collision required. Predicting a rough location and size for a cold region is impressive, but it is not the same as an airtight, 1 in a billion bullseye, and the significance of the match is contested. So we have, here, 2 honest sentences that must be held together. A serious physicist predicted a scar, and the scar appeared. And also, the scientific community has not concluded that this proves another universe exists. Both are true. The wonder and the caution live in the same room. But the equation she wrote did not stop at predicting where the scar would be. They also described how it would form. They described the actual mechanics of what happens when 2 universes touch, and it is not what you would expect. They do not shatter like glass. They do something quieter, and in its own way, far more disturbing. To feel what a collision between realities would really do, we have to leave the map behind and go stand inside the early universe itself. Part 6. The Siphon. When we imagine a collision, we picture impact. 2 cars meeting on a highway, metal crumpling, glass flying. But universes, if they collide at all, do not collide like solid objects. According to the models we're following tonight, they interact through the one thing they can share across the boundary between them, which is gravity. And gravity does not crash. Gravity pulls. Think about how gravity actually works. It is the gentle, patient force that draws mass toward mass. The Earth pulls you down into your chair. The sun holds the Earth in its long, slow circle, and gravity has a peculiar and important property. It is relentless, and it reaches. It does not stop at the surface of an object or the edge of an atmosphere. It thins with distance, but it never truly ends. In the models of the multiverse we're exploring, gravity is imagined as the one force that can leak across the boundary between one universe and another, the single language 2 separated realities can still speak to each other. So in this picture, when our young bubble universe brushed against a neighbouring bubble, they did not simply bounce apart like billiard balls. For a brief cosmic instant they touched and they interacted, and the other universe, whatever it was, had mass. Enormous amounts of it, and wherever there is mass there is gravity, reaching. So the neighbouring universe reached into ours, not with a fist, but with a pull. I want you to stand inside this now, because the early universe is a place your intuition has no map for, and the only way through is to feel it. Close your eyes and take yourself back to the first minutes after the beginning. There are no stars here. There are no planets, no atoms even, not yet. There is only a searing, dense fog of plasma, a fluid of light and bare particles hotter than the core of any sun that will ever exist, filling all of space, glowing, churning, pressing in every direction at once. This is what everything you will ever love is made of, in its very first form. Now imagine that you are floating in this fluid, and that somewhere beyond the edge of your reality, closer than you could ever point to, another entire universe drifts near. You cannot see it. You will never see it. But you begin to feel it, because its gravity has crossed the wall, and it does not tug at you gently. It grabs the plasma around you, the raw material of every future galaxy, and it begins to drag. The fluid streams past you, pulled toward a boundary you cannot perceive, siphoned away toward the point where the 2 worlds are touching. The heat goes with it, the matter goes with it, and when the pull finally releases and the 2 universes drift apart again, they leave behind a hollow. A region where the building blocks of reality were simply drawn out and carried off, like water pulled up a straw. Open your eyes. That, in this model, is why the Eridanus supervoid is so empty. It is not a random quiet spot where galaxies happen not to form. It is a place that was drained. Think of it this way. Take a vacuum cleaner nozzle and press it against a stretched sheet of fabric. The fabric is our universe, the flat surface of everything we know. The vacuum is the gravity of the neighbouring reality. When the nozzle touches down, it does not tear a hole. It pulls. It creates a bulge, a dimple, and it draws everything loose toward that single point of contact. In the early universe, when everything was still fluid and nothing had yet frozen into stars, that pull would have worked with terrible efficiency. It would have grabbed the plasma, the gas, the dark matter, the raw potential of thousands of future galaxies, and hauled it all toward the wall. It would have siphoned the ingredients of reality straight out of that sector of the sky. This is the reading that turns the void from a mystery into a crime scene. the 10,000 galaxies that should be sitting in that enormous region are not missing because they failed to form. In this story, they are missing because the material needed to build them was stolen, pulled away before it could ever gather into stars by the gravity of a larger, heavier reality passing next door. We are looking, in this telling, at a region of space that was strip-mined by the neighbours, and once again I owe you the counterweight, because it is easy to get carried off by an image this vivid. The mainstream view does not need any of this. In the ordinary picture, great voids form gradually and naturally as gravity slowly herds matter out of the emptier regions and into the denser ones over billions of years. No outside universe required, no siphon, no wall. The cosmos is full of voids of many sizes, and the existence of a large one is not by itself evidence of a collision. What we have is a remarkable region that admits a remarkable interpretation, alongside an ordinary one that most physicists still prefer. I keep saying this because it is the truth, and because the whole point of walking to the edge is knowing where the edge actually is. But suppose, just for the length of this next thought, that the collision reading is right. If a neighbouring universe was strong enough to reach across the wall and drag an entire cluster of unborn galaxies away from us, then it raises a sharp and simple question. Was it a single event? A one-time brush between two bubbles never to be repeated? Or if we look more carefully at the oldest light, will we find that the collision was not a single accident at all, but only the first of many? To answer that, someone had to teach a computer to hunt for a very particular shape hidden in the noise of the beginning, and when the computer went looking, it did not find one wound. It found a pattern. Part 7. Dents all over the car. While some physicists were focused on explaining the single scar of the cold spot, a team at University College London, led by the astrophysicist Stephen Feeney, decided to ask a broader and more chilling question. They did not just want to understand one wound. They wanted to know whether the patient had other injuries. Feeney understood something important about human perception. We are wonderful at inventing patterns and terrible at finding real ones buried in noise. We see faces in clouds and animals in wallpaper, and at the same time we can stare straight at a genuine, subtle structure and miss it completely because it does not shout. So rather than trust human eyes to scan the sky, his team built a computer algorithm, a piece of software designed to hunt for one specific shape in the cosmic microwave background. Not a blob, not a cold patch, a ring. Why a ring? Because physics is consistent and consistency makes predictions. If our universe really is a bubble floating among other bubbles, then a collision with a neighbour should not leave a shapeless smear. It should leave something with structure, something with symmetry. Think about throwing a stone into a perfectly still pond. The impact does not make a random splotch. It makes a circle, a ripple that expands outward in a clean expanding ring. If the early universe was a fluid, and if another bubble struck it, the collision should have sent a circular shockwave of temperature variation rippling outward through the cosmos, freezing into the ancient light as a faint round trace. So Feeney's algorithm swept across the entire sky, patiently, looking for those faint circular signatures that no human eye could reliably pick out of the static. There is something worth pausing on in how carefully this was done, because it tells you these were serious people, not dreamers chasing a headline. A collision between two bubble universes would not leave just any circle. The mathematics predicts a specific kind of pattern, a region where the temperature is disturbed in a particular way inside a sharp circular edge, with the edge marking how far the shockwave from the collision had spread by the time the ancient light was released. So the team did not simply hunt for round shapes, which the eye invents everywhere. They built a template of exactly what a real collision signature should look like, mathematically, and then they let the computer test the entire sky against that template, patch by patch, asking at each spot how well the data matched the precise prediction. This is the difference between seeing a face in the clouds and actually measuring whether a face is there. One is imagination. The other is a number, a probability, a quantity you can defend or be forced to abandon. And that discipline is exactly why their honesty at the end carries weight. If they had found nothing shaped like a circle, that would prove little, since the signal could be too faint. But they found candidate circles, ran them through the full statistical machinery, and reported that the matches were no stronger than what random fluctuations would produce on their own. They could have spun that into a discovery. The raw ingredients for a dramatic headline were sitting right there. Instead, they told the truth, which is that the sky did not give them enough to claim anything. I find that quietly moving, in its way. It is what it looks like when people love the question more than they love being right. And the computer found candidates. It identified several distinct circular patterns embedded in the radiation of the early universe, features that had the rough ringed shape a bubble collision might produce. For a moment the implication was dizzying, because if the cold spot is a single bruise, you might dismiss it as a freak accident. But a set of rings is a different story entirely. Let me put it in terms you can feel in your gut. Imagine walking out to your car in the morning and finding a single dent on the bumper. You would shrug. Maybe a stray shopping cart rolled into it in the parking lot. Bad luck, nothing more. But now imagine walking out and finding dents on the hood, and the doors, and the roof, and the trunk, all over the car. At that point you stop thinking about luck. You stop looking for the one shopping cart. You realise your car has been through something. A hailstorm maybe, or a demolition derby. The pattern rewrites the story. One dent is an accident. Dents everywhere is a history. In this reading, the presence of multiple circular patterns would suggest that our universe has not been struck once, in a single unlucky collision, but repeatedly. That we are less like a car parked safely in a garage and more like a battered vehicle that has been driving through a hailstorm of other realities, taking hit after hit over cosmic time. We would not be floating in a calm and empty void. We would be navigating a dense, churning foam where universes are constantly jostling, brushing, merging and bouncing off one another, and the history of our own world would be written in the accumulated scars of those impacts. We would be, in the most literal sense, well-travelled and well-dented. It is a genuinely vertiginous idea, but I have to stop us here, harder than I have stopped us anywhere yet, because this is the point in the story where excitement most wants to outrun the evidence. Stephen Feeney's team did find candidate circular patterns. That part is true, but when they carried the analysis all the way through, applying the full statistical rigour, their own conclusion was cautious and, frankly, deflating for anyone hoping for a headline. The patterns they found were consistent with what you would expect from ordinary random fluctuations in the cosmic microwave background. In other words, the rings were not statistically compelling evidence of bubble collisions. They could not rule the collisions out, but they could not confirm them either. The honest scientific verdict was a shrug, not a revelation. The dents on the car, when examined carefully, might just be the ordinary texture of the metal seen up close. I tell you this not to spoil the wonder, but to protect it, because a wonder built on a false claim collapses the moment you lean on it, while a wonder built on the truth can hold your weight forever. And the truth here is quietly remarkable even without the collisions. We built machines and wrote algorithms capable of scanning the entire sky for the fingerprints of other universes. We asked the oldest light in existence whether it carried the marks of a crowded cosmos, and the light gave us an answer that was honest and unsatisfying and exactly what good science sounds like. Maybe. We cannot tell yet. Keep looking. So we have a scar that might be a crash site, and a set of rings that might be more of them. And in both cases, the mainstream verdict is not yet, not proven. Hold your horses. If the story ended there, it would be a beautiful maybe and nothing more. But the story does not end there, because the next piece of evidence is not about the distant past at all. It is about right now. It is about the possibility that we are not merely sitting inside a universe that was struck long ago, but that we are at this very moment being pulled. That the whole neighbourhood of galaxies, including everything you have ever seen in the night sky, is moving together in a single direction towards something none of us can name. There is, some claim, a current running through the cosmos, and we are in it. Part 8. The River We Cannot See. Before we can talk about being pulled, we need a way to know we are moving at all, and that is harder than it sounds. To do physics on the scale of the whole universe, you need a map, and every map needs a fixed point, a north to orient yourself against. In our cosmos, that north is not a star or a galaxy, because everything made of matter is itself in motion. The fixed reference is the cosmic microwave background, the ancient light we have been talking about all night. It fills every direction, a faint even glow left over from the beginning, and it gives us the closest thing there is to an absolute frame of rest for the entire universe. Here is how you use it. If you're sitting perfectly still relative to that ancient light, its temperature looks exactly the same in every direction. But if you're moving, something subtle happens. The light ahead of you gets very slightly warmer and bluer, bunched up by your motion, and the light behind you gets very slightly cooler and redder, stretched out. It is the same effect that changes the pitch of an ambulance siren as it races past you, rising as it approaches and falling as it recedes. It is called the Doppler effect, and the cosmic light lets us read our own motion off of it, like a speedometer built into the sky. And when we do read it, we find that our own galaxy is indeed moving, at a well-measured speed of roughly 600 kilometers per second relative to that ancient light, toward a particular region of the sky. That much is solid, established, and not in dispute. We are moving. The question is why, and what happens when you ask the same question of everything else. Because there is a rule that says the answer should be boring. It is one of the most important rules in cosmology, and we already met its cousin earlier tonight. It is called the cosmological principle, and it says that on a large enough scale the universe is the same everywhere and in every direction, that matter is scattered about like gas in a sealed box with no special currents and no privileged flow. Under this principle, galaxies should move a little like a swarm of bees. Each individual bee buzzes this way and that, tugged by its nearest neighbours, but the swarm as a whole stays put. If you measured the motion of thousands of galaxies scattered across the sky, their little random velocities should cancel out. Some drift left, some drift right, some race forward, some fall back, and when you add it all up, the average motion of the universe should come out to zero. Stillness. That is not a minor detail. It is baked into the equations we use to weigh and age the cosmos. But in 2008, an astrophysicist at NASA named Alexander Kashlinsky and his team decided to test that stillness directly, and they used a wonderfully clever tool to do it. You cannot just look at how fast distant galaxies appear to recede, because that motion is dominated by the ordinary expansion of space, and it drowns out the subtle drift they wanted to measure. So instead of watching the light the galaxies emit, they watch the shadows they cast in the ancient background light. The technique is called the kinematic Sunyaev-Zeldovich effect, and the idea behind it is elegant. As the cosmic background light streams through a massive cluster of galaxies, it scatters off the hot electrons in the cluster's gas. If the cluster is moving toward us, that scattering gives the light a tiny blue nudge. If it is moving away, a tiny red drag. This nudge has nothing to do with the expansion of the universe. It is a direct reading of the cluster's own bulk motion through space, a clean speedometer for something billions of light years away. I want to slow down on how strange and wonderful that measurement is, because it is easy to skate past and it deserves better. Think about what is actually happening. A photon of light was released almost 14 billion years ago, in the fire of the young universe. It has been travelling ever since, across distances the mind cannot hold, and at some point in that long journey, it passed through a cluster of galaxies, a churning cloud of gas so hot its atoms have been stripped bare into a plasma of free electrons. The photon glanced off one of those electrons, and in that glancing blow it picked up or lost a tiny sliver of energy depending on which way the whole cluster happened to be drifting. Then it continued on, carrying that faint bruise of information, until it fell into a detector we built and lifted above the atmosphere. And from that almost invisible shift, we can read the motion of a structure so far away and so enormous that it holds 1,000 galaxies. We are in effect reading the speed of a distant continent by the way the light bends as it crosses it. That we can do this at all is one of the quiet miracles of modern science. And the cosmic background light behind all of this deserves one more moment of attention, because it is doing something no ordinary landmark can. Everything else in the universe is moving. Stars orbit galaxies, galaxies swarm within clusters, clusters drift within superclusters. There is no fixed post anywhere to nail your map to, no lighthouse standing still. Except this. The ancient glow left over from the beginning fills all of space evenly, and because it belongs to no single object, it comes closest to a universal frame of rest, a still surface against which all the motion can finally be measured. When you read your own speed off of it, you are, in a real sense, measuring your motion against the universe as a whole. And what it tells us is that nothing is truly at rest. Not your chair, not your city, not the ground under the ocean, not the galaxy wheeling around you. Everything is going somewhere. The only question is whether it is going there together. Kashlinsky did not measure one or two clusters. His team gathered data on hundreds of them, and in later work more than 1,000 massive galaxy clusters spread across the sky. According to the standard picture, the motions of 1,000 widely separated clusters should look like static, random directions averaging out towards zero. But that is not what Kashlinski reported. He reported that the clusters were moving together, not randomly, but coherently, in lockstep, all drifting in roughly the same direction at a speed of hundreds of kilometers per second, in some versions approaching 1,000. They were not behaving like bees in a swarm. They were behaving like debris caught in a single river, all carried the same way by a current none of them could see. He called it dark flow. Now feel what that claim would mean if it were true. It would mean that a huge swath of the visible universe, thousands of galaxies across billions of light years, is not drifting randomly but sliding together as one toward a single point in the sky. It would mean the cosmological principle, the assumption of a directionless, currentless universe, is quietly broken. It would mean the floor of the cosmos is not flat. It is tilted, and everything on it, including us, is beginning to roll downhill toward whatever is waiting at the bottom. And here, once more, honesty. Dark flow is not an accepted result. It is one of the most hotly contested claims in modern cosmology. When the Planck team analysed the same kind of signal with their own data, they found no statistically significant flow of this kind. Their conclusion was that the motions of distant clusters are consistent with the ordinary, boring standard picture, and that the dark flow, if it is there at all, is far smaller and less certain than the dramatic version suggests. So we have a genuine disagreement between serious teams of scientists using overlapping data, arriving at different answers about whether the entire sky is drifting. That is not a settled discovery. It is a live argument, and the weight of current evidence leans against the dramatic reading. Let me step back for a moment, because we have covered a great deal, and it is worth gathering the pieces before we press on. We began with an assumption that the universe is smooth. We found it lopsided. We found a cold scar and, beneath it, an immense emptiness that gravity struggles to explain. We found a physicist who predicted that scar from a theory of colliding universes, and we found rings that might be more collisions, though the evidence for both fell short of proof. And now we have found a possible current, a claim that we are being carried, that also falls short of proof. Notice the shape of this. Every rung of the ladder is real enough to climb onto, and every rung is wrapped in an honest maybe. That is what the true edge of knowledge feels like. Not a wall, and not an open door, but a fog you can walk into only so far before the ground gets uncertain under your feet. But suppose, for the next stretch of the climb, the current is real. Suppose something is pulling. Then the obvious question becomes the one every physicist asks when they see motion. Where is the drain? If we are flowing, we must be flowing toward something, and gravity always has a source. So astronomers followed the direction of the pull, out past the galaxies we know, hunting for whatever monster sits at the bottom of the slope. And what they found out there only deepened the mystery. Part 9. Hunting the drain. If a river is flowing, there is a low place it is flowing toward. So astronomers took the direction of our galaxy's motion, that well-measured drift of about 600 kilometers per second, and they traced it out across the sky to see what was pulling. The line pointed toward a patch of sky between the constellations of Centaurus and Hydra, and immediately they ran into a frustrating obstacle, one that has haunted this particular corner of astronomy for decades. The direction we are being pulled points almost straight through the plane of our own Milky Way, through the thick band of stars and dust that we call the zone of avoidance, because it is the region where our own galaxy's glare blocks our view of whatever lies behind it. We were, in effect, trying to see the thing dragging us while staring directly into our own headlights on a foggy night. Driving down a cosmic highway at enormous speed, with a windshield caked in dust, trying to make out the shape of the road ahead. But dust that blocks visible light is more transparent to other wavelengths, and using radio and infrared telescopes that can partly pierce the haze, astronomers found their first suspect. They named it the Great Attractor. It is a gravitational anomaly sitting roughly 250 million light-years away, a concentration of mass anchored by a large cluster of galaxies called the Norma Cluster, and it is clearly tugging on everything in our neighbourhood, including us. For a while, people thought this was the answer. We were simply rolling into a local valley, a nearby pothole in the fabric of space. Mystery solved, except that when astronomers carefully weighed the Great Attractor, the arithmetic did not balance. It is big, yes, but it is not nearly heavy enough to account for the full motion of everything being pulled in its direction. It is like watching a freight train roll across the landscape and being told that the thing towing it is a single household magnet. The scale is wrong. The great attractor is real, and it is pulling, but it is not the whole story. Something bigger had to be hiding behind it. So they looked further, past the great attractor, deeper into that same region of the sky, and they found a giant. They found the Shapley supercluster, the single largest concentration of galaxies in the nearby universe, a titan holding the mass of thousands of galaxies packed into a relatively compact volume. Here, surely, was the engine. Here was something massive enough to be doing the pulling, and it does contribute. But when astronomers looked closely at the motion again, a subtle and stubborn problem appeared, and this is where the ordinary story starts to strain. If a single massive object were doing all the pulling, then the objects closest to it should be falling toward it fastest, and objects farther away should feel a weaker pull and move more slowly. That is simply how gravity works. It weakens with distance, so the tug should fade as you move away from the source. But in the most dramatic readings of the flow data, the pull did not seem to fade the way it should. Galaxies at very different distances appeared to be moving at similar speeds, as if the current did not care how far you were from any particular attractor. And a pull that does not weaken with distance is a strange and troubling thing. It hints that the true source is not any single object we can see, but something so sprawling and so far away that its gravitational slope looks almost flat across the whole region we can measure. Not a nearby valley, a horizon we're all sliding toward. Now, I have leaned into the dramatic version to let you feel the pull of it, so let me set it right, because the honest picture here is actually one of the great triumphs of modern astronomy, and it does not require anything from outside our universe at all. In 2017, a team led by the cosmologist Yehuda Hoffman, together with Brent Tully and others, completed a map of our cosmic motion that filled in the missing half of the picture. We had been obsessed with what was pulling us from in front, but gravity is a tug of war, and they realized we had ignored what was behind us. They found that the region of space behind our motion is not average. It is unusually empty, an enormous under-dense region almost devoid of galaxies, and in a universe where matter pulls, a great emptiness effectively pushes because there is less gravity on that side to hold you back. They named it the dipole repeller. On one side, the attractors and superclusters pull us forward. On the other, the great void behind us gives us a gentle shove. Add them together, and you can account for our motion using nothing but the ordinary distribution of matter and emptiness in our corner of the cosmos. This whole flowing structure, the attractors and the repeller and everything caught between them, is part of a supercluster of galaxies that Tully's team mapped and named Laniakea, a Hawaiian word meaning immeasurable heaven. We live on the outskirts of it, and we are slowly sliding down its gentle internal slope, drawn along by the visible architecture of our own local universe. I find that genuinely beautiful, and I want to give it its due, because it is the grounded answer, and it is real. The most solid version of We Are Being Moved needs no other reality, no leaking wall, no neighbouring bubble. It needs only the honest tug of the biggest things we can see and the quiet push of the emptiness behind us. That is the baseline. That is what is actually established. And the speculative story, the one about a monster beyond the horizon, has to climb over that grounded explanation before it earns the right to be taken seriously. Most cosmologists would tell you it has not. But I also want to be fair to the strangeness, because the strangeness has not entirely gone away. There remain genuine open questions in this field about the larger scale flows in the universe, about whether some bulk motions are a little larger than the standard model comfortably predicts, and these are argued about in the literature by serious people right now. The mainstream has a good explanation for our local motion. It is less settled whether the very larger scale flows are fully accounted for, and that unsettledness is exactly the crack the speculative story wants to widen. When a pull seems not to fade with distance, one reading is that you have simply not mapped the sources yet. Another reading, the one we are following tonight, is that the source lies beyond the edge of everything you can ever see. And that phrase, beyond the edge of everything you can see, is not loose talk. It points at something real and hard about our situation, something we have to confront before we can go any further. Because the universe has an edge, in a very specific sense. Light travels at a finite speed, and the universe is only so old, so there is a maximum distance from which light has had time to reach us since the beginning. That boundary is called the cosmic horizon, and everything beyond it is for now completely dark to us. We cannot see it. We may never see it. But here is the thing that keeps this story alive. Gravity does not care about that boundary. Light cannot cross it to reach us, but gravity, the curvature of space itself, can ripple across it freely. Which means that if there is a titanic something sitting just beyond our horizon, we could never see it, and yet we might feel its weight, tilting the floor of the entire cosmos, pulling us toward an edge we were never meant to know was there. To understand how something outside our horizon, or outside our universe entirely, could reach in and touch us, we have to stop talking about telescopes and start talking about dimensions. We have to fold up space itself. Part 10. The Folded Up Fifth Dimension. In 1919, a virtually unknown mathematician named Theodore Kaluza sent a letter to Albert Einstein that would quietly reshape physics. At the time, Einstein was the most famous scientist alive, celebrated for general relativity, his theory that describes gravity not as a force but as the curvature of space and time. But there was another force that nobody could connect to gravity, and it was the force of light itself, electromagnetism. Gravity and electromagnetism seemed like two entirely different languages, two separate sets of rules with nothing to say to each other, and Kaluza did something that was either naive or brilliant, and turned out to be brilliant. He took Einstein's equations of gravity, which live in our familiar 4 dimensions, 3 of space and 1 of time, and he simply added a 5th. He did not know what it was. He did not claim to see it. He just wrote it into the mathematics, an extra direction, and worked through what happened. What happened was close to magic. When Kaluza solved the equations of gravity in 5 dimensions instead of 4, the extra pieces did not turn into nonsense. They rearranged themselves on their own into the exact equations of electromagnetism that James Clerk Maxwell had written down decades earlier. Gravity in 5 dimensions contained light. The 2 languages were revealed to be dialects of the same deeper tongue. It was the first successful unification in the history of physics, the first time 2 forces that looked completely unrelated were shown to be different faces of one thing. And it suggested, almost as a side effect, that light and gravity might simply be the same phenomenon, vibrating in different dimensions. There is a small human detail in this story that I love, because it shows how even the greatest minds hesitate at the edge of a strange idea. When Kaluza sent his result to Einstein, Einstein did not immediately embrace it. He sat on the paper for about 2 years, turning it over, unsure whether adding an invisible dimension was a stroke of genius or a step too far. Eventually he helped get it published, but you can feel, across the century, the same hesitation you're probably feeling right now. An extra dimension is not a small thing to accept. It asks you to believe that the world has a direction in it that you have never once perceived, that has been there your whole life, threaded through the space in front of your face, and that you have simply never had the senses to notice. Einstein hesitated at that. So it is entirely reasonable if you do too. The point is not to swallow it whole. The point is that the mathematics, when you follow it honestly, keeps handing you this 5th direction whether you ask for it or not. And the reason we cannot feel it, if it is there, comes back to how small Klein said it must be. When physicists estimate the size of a compactified dimension, in the original picture, they arrive at something almost absurdly tiny, far smaller than an atom, far smaller than the nucleus inside an atom, down near the smallest meaningful scale in all of physics. At that size, the extra dimension is not a place you could ever go. You could not put so much as a single particle into it and have room to move. It would be less like a hidden hallway, and more like the thinnest possible seam stitched into every point of space, everywhere at once, closed into a loop so small that from where you stand it may as well not have a length at all. And yet, in the mathematics, that impossibly small seam is exactly where gravity and light quietly become the same thing. The smallest hidden direction imaginable, doing the deepest unifying work in physics. That tension between how tiny it is and how much it might be responsible for is what makes people keep chasing it. But this beautiful result came with an obvious and embarrassing problem. If there is a 5th dimension, where is it? Why can you not point to it, walk into it, throw a ball down it? In 1926, a physicist named Oscar Klein offered an answer that we still use today. He proposed that dimensions come in 2 kinds, extended and curled up. The 3 dimensions of space we know, up and down, left and right, forward and back, are extended. They stretch out as far as we can tell for billions of light years. But the 5th dimension, Klein said, is not like that. It is rolled up, compactified, wound into a circle so tiny that we cannot perceive it or enter it. The classic image for this is a garden hose. Picture a long hose lying across a lawn, and imagine you are looking at it from very far away from an airplane. From that height, the hose looks like a simple one-dimensional line, a thread stretched across the grass. But now shrink yourself down to the size of an ant crawling on that hose, and you discover something the airplane missed. The hose has a 2nd dimension you could not see from above. You can walk along its length, yes, but you can also walk around its circumference, looping around and around the tube. That 2nd dimension was there the whole time. It was just too small to notice from a distance. Klein argued that the 5th dimension is like the circumference of the hose, curled into a tiny loop at every single point in space, smaller than an atom, far too small for us to see or step into, but genuinely there. A hidden direction, wound up inside the emptiness in front of your face. I want to be clear that this is not fringe science. This mechanism, compactification, the idea that extra dimensions can be rolled up too small to see, is the mathematical bedrock of almost all of modern theoretical physics. Without it, the equations of string theory simply do not work. So the notion that there might be more dimensions than the 3 you move through, folded up inside the fabric of space, is not a wild claim. It is a foundation that thousands of working physicists build on every day. The wild part comes later, when we ask what might be hiding in those extra folds. Because by the 1990s, this line of thinking had run into a crisis of its own. The dream of unification that Kaluza had started had grown into string theory, but string theory had multiplied into 5 different versions, 5 distinct mathematical descriptions of the universe, each internally consistent, each requiring extra dimensions, and each subtly different from the others. It was as if we had 5 different maps of the same territory, all of them apparently valid, none of them agreeing. That is not how a final theory is supposed to look. A final theory should be unique. Then, in 1995, at a conference in California, the physicist Edward Witten stood up and did something that reorganized the entire field in what became known as the second superstring revolution. Witten showed that the 5 competing versions of string theory were not 5 different theories at all. They were 5 different views of a single larger mathematical object, 5 windows into one underlying structure. He called that structure M theory. Nobody agrees on what the M stands for: membrane, magic, mystery, matrix, take your pick. But to make the 5 theories fit together into one, Witten had to do something bold. He added another dimension. He took string theory from 10 dimensions up to 11. And in that 11th dimension, something changed about the strings themselves. A string is a one-dimensional object, a tiny vibrating line. But give it room to stretch in an extra dimension, and a line can widen into a sheet. Stretch a sheet, and it can thicken into a volume. This gave birth to a new object at the heart of M theory, the brain, short for membrane. And here is the idea that everything tonight has been building toward. According to M theory, our entire observable universe, every star, every galaxy, every atom in your body, may be stuck to a single 3-dimensional brain, an enormous thin sheet of reality floating inside a larger, higher dimensional space. That larger space has a name. Physicists call it the bulk, or hyperspace, and our brain is just one surface within it. Think of a loaf of sliced bread. Our universe, in this picture, is a single slice. We can move freely within our slice, left and right, up and down, forward and back. But we cannot step out of the slice into the space around it. We cannot reach the crust or the air or the neighbouring slices. We are confined to the surface, the way a drawing is confined to the page, and this quietly redefines the word universe. We used to think the universe was everything that exists, the whole of reality. But in M theory, our universe might be only an island, a single slice, and the bulk is the ocean it floats in. The ocean is immense and deep and mostly dark. But oceans are rarely truly empty. And if our slice is just one of many, then the obvious question, the one that makes the back of your neck prickle, is what is in the next slice over. How close is it? And what, if anything, could reach across the gap between the pages? To answer that, we first have to understand why we are stuck to our slice in the first place, and why one single force is not. Part 11. Why we're glued to the screen. If the bulk is real, if there is a huge higher dimensional space stretching out just beyond the surface of our universe, then a fair and frustrated question rises up. Why can we not see it? Why can we not simply turn our heads in the right direction and look into the fifth dimension, make out the other slices of the loaf? The answer lies in the deep structure of matter itself, and it is one of the most elegant and claustrophobic ideas in all of string theory. Everything in the universe, in this picture, is made of tiny vibrating strings of energy. An electron is a string humming at one frequency. A quark is a string humming at another. The endless variety of particles is just the endless variety of notes a string can play. But strings come in two fundamental shapes, and this difference in shape is what decides your freedom. Some strings are open, like a short length of thread with two loose ends. Others are closed, forming a complete loop with no ends at all. And it turns out that almost everything you are made of, the protons, the neutrons, the electrons, all of it, is built from open strings, threads with two loose ends. Here is the rule that quietly imprisons us. The loose ends of an open string cannot float freely in the higher dimensional bulk. They have to be anchored to something. Specifically, they have to be attached to a brain. Picture the hairs on your arm. Each hair can wave around, bending this way and that in the breeze, but the root of every hair is planted in your skin. The hair cannot simply detach and drift away into the room. In exactly the same way, every particle of ordinary matter in our universe has its endpoints rooted to our three-dimensional brain. We are stuck to the surface of our own reality the way flies are stuck to flypaper. We can slide around on the sheet, but we cannot lift off of it. And the true prison, the deepest part of it, is not about matter. It is about light. The particles that carry light, photons, the things that let you see anything at all are also open strings. Their ends too are pinned to our brain, and this has a consequence that is almost unbearable when you sit with it. Light can only travel along the surface of our universe. It cannot leave it. You cannot shine a flashlight into the bulk because the beam has nowhere to go but along our own sheet. It is physically impossible for a photon to travel off our brain and into the higher dimensional space. And that is the real reason the bulk is invisible to us. It is not that there is nothing out there. It is that we are blind to it by the very nature of the light we see with. Let me put you inside that prison for a moment, because I think it is the only way to feel how strange our situation might be. Imagine you are a character painted on an enormous movie screen. You're made of light and colour on that flat surface, and you can move anywhere across it, left, right, up the screen, down the screen, into what feels to you like distance. Your whole world is the screen, and it feels complete. It feels like everywhere. Now imagine that just a few feet in front of the screen sits the projector, and beside it, an entire audience, a whole room of people, a whole dimension of space and life. They are close. They are almost close enough to touch, but you cannot point toward them, because the direction they lie in, off the surface of the screen, is a direction that does not exist inside your two-dimensional world. You could search your entire flat universe forever and never find the way out, because the exit is perpendicular to everything you know. The projector is inches away, and it might as well be in another world, because in a sense it is. That, in this model, is us. We are patterns of light and matter smeared across a three-dimensional sheet, and the bulk, with whatever it contains, might be inches away in a direction we can never face. We are living on a screen, trying to see the audience, and the light we would need to see them with is trapped on the screen along with us. But there is one exception, one thing in all of physics that refuses to be confined to the brain. And you can already guess what it is, because it has been the quiet hero of this entire story: gravity. According to string theory, the particle that carries the force of gravity, called the graviton, is not an open string with loose ends. It is a closed loop, a complete circle with no ends at all. And that single geometric difference changes everything about the prison. Because a closed loop has no loose ends, it has nothing to anchor to the brain. It cannot be pinned down the way an electron or a photon is, which means gravity is free. Free to slip off the surface of our world, free to drift out into the bulk, free to leak into the fifth dimension. This is not just a poetic flourish. It may be the answer to one of the deepest and most frustrating puzzles in all of physics, the mystery of why gravity is so absurdly, ridiculously weak. Think about a small refrigerator magnet. that tiny scrap of metal can hold up a paperclip against the gravitational pull of the entire planet Earth. The whole Earth, all of it, is pulling that paperclip down, and a coin-sized magnet beats it without effort. Gravity is roughly 10 to the 36th times weaker than electromagnetism. That is a 1 with 36 zeros after it. It is a gap so enormous it makes no sense. Why would nature build one force so overwhelmingly feebler than the others? String theory offers a startling answer. Maybe gravity is not weak at all. Maybe gravity is just as strong as the other forces, and the reason we feel only a faint whisper of it is that most of it is leaking away, draining off our brain into the extra dimensions, diluting into the bulk like sound passing through a thin wall into the next room. We feel the muffled remainder, and we call it weak, when in truth the full force is escaping into a space we cannot see. And now we arrive at the thought that this entire section has been walking toward, the corollary that turns a beautiful idea into an unsettling one. If gravity can leak out of our universe into the bulk, then the process must run both ways. A wall that lets something out can let something in. If our gravity is draining into the fifth dimension, then the gravity of whatever is out there in the bulk, another brain, another universe, some massive structure drifting in the dark, can leak into us. We might never see our neighbours. Their light can never reach us, and ours can never reach them. But if they have mass, and mass makes gravity, and gravity crosses the wall, then we should be able to feel their weight. The wall between realities, the phrase I offered you at the very beginning as a metaphor, is starting to become something else. It is starting to become a real surface, a membrane, and the disturbing thing about it is not that it is solid. The disturbing thing is that it is porous, and if it is porous, then the only question left is how close the neighbours actually are. The answer, according to some physicists, is far, far closer than you would ever want them to be. Part 12. A millimetre away. When we imagine parallel universes, we tend to place them impossibly far away, separated from us by unbridgeable gulfs, other bubbles drifting billions of light-years off in some cosmic foam. But in 1999, two physicists, Lisa Randall and Raman Sundram, published a pair of papers that quietly demolished that comfortable sense of distance. They built a mathematical model of a warped five-dimensional geometry, and in it, our universe was not a lonely bubble far from its neighbours. It was more like one wall in a narrow room, and according to some versions of this kind of thinking, the extra dimension separating us from a neighbouring reality might not be enormous at all. It might be almost unimaginably thin. In the boldest large-dimension scenarios, the gap between our brain and a neighbouring one could be as small as a fraction of a millimetre. I want you to hold that scale in your mind, because it refuses to stay abstract. A millimetre is the thickness of a coin's edge. It is less than the width of your own skin. If these models were right in their most dramatic form, then the multiverse would not be a distant place you would need a starship to reach. It would be superimposed right on top of you. There could be an entire other universe, with its own stars and planets and laws, hovering less than the width of a fingernail from your face, right now, in a direction you cannot turn toward. The reason you cannot see it or touch it is not distance. It is that you are trapped in three-dimensional space, like that character on the movie screen, and the neighbouring wall lies off the surface perpendicular to every direction you know. I have to plant the honesty flag firmly here, because this is one of the places the popular story runs well ahead of the evidence. The millimetre figure comes from a specific family of large extra-dimension models, and here on Earth we have tested gravity at small distances with exquisitely sensitive instruments, torsion balances that can feel the faintest deviation from the normal law of gravity. Those experiments have found no sign of extra dimensions down to distances well below a millimetre, which means the true allowed gap, if it exists at all, is far smaller than the dramatic version claims. So keep the image, because it is a real idea that real physicists proposed. But keep the caveat beside it. The neighbour is not confirmed to be a millimetre away. The neighbour is not confirmed to exist. What is real is that the mathematics permits a nearby wall. An experiment has been steadily pushing that wall thinner and harder to find. Still, suppose there is a neighbour. What happens to two membranes floating parallel in the bulk, a hair apart? Do they simply hang there forever, politely, never touching? Physics suggests they might not, and the reason comes from one of the strangest proven facts about empty space. In 1948, the physicist Hendrik Casimir predicted that if you take two ordinary uncharged metal plates and bring them extremely close together in a vacuum, they will feel a mysterious force pulling them toward each other. Not magnetism, not static, something deeper. The reason is that the vacuum is not truly empty. It seethes with quantum fluctuations, a restless froth of energy at the smallest scales. Between two closely spaced plates, only certain sizes of fluctuation fit, while outside the plates fluctuations of every size press in. That imbalance creates a net push from outside, squeezing the plates together. It sounds like fantasy, but it is not. The Casimir force has been measured in the laboratory. Engineers who build machines at the scale of nanometers have to account for it, because it makes tiny parts stick together. It is real. Now, some physicists have taken that proven effect and asked a vertiginous question. If two metal plates get squeezed together by the vacuum, what about two brains, two whole universes floating parallel in the bulk a tiny distance apart? Would the quantum fluctuations of the fifth dimension generate a Casimir-like force between entire realities, an inexorable pressure drawing them together? In this speculative picture, two parallel universes could not simply hover peacefully forever. The vacuum itself would push them toward each other, slowly at first, then faster as the gap narrowed and the force grew, like a cosmic zipper closing. And some have wondered whether the very motions we struggled to explain earlier, the flows and the pulls, might be our entire brain bending and sliding under the pressure of an approaching wall. I flag that last leap as the speculation it is, but the seed of it, the Casimir force, is one of the most solidly established facts in physics. And here is where the story stops being about distant walls and starts being about the room you are sitting in, because there is a candidate for what might be sharing our space that does not require another universe at all. It only requires that we have been wrong about what fills our own. Go back to 1956, when two physicists, Tsung-Dao Lee and Chen-Ning Yang, discovered that nature is not perfectly symmetric between left and right. In certain particle decays, the universe shows a genuine handedness, a preference that shocked physicists to their core, because it had always been assumed that the laws of physics could not tell left from right. To restore some balance to the equations, some theorists proposed a radical idea. What if, for every kind of particle we know, there exists a mirror version, a hidden partner sector that is the reflection of our own? This is the mirror matter hypothesis, developed over the years by physicists including Robert Foote and Zurab Ciligadze, and the crucial thing about it is what makes it so eerie. Mirror matter is not antimatter. Antimatter is dramatic and destructive, annihilating in a flash of energy the instant it touches ordinary matter. Mirror matter would do nothing of the kind. It would simply ignore us. Mirror particles would have their own mirror version of electromagnetism, their own mirror light. That means mirror matter could form mirror atoms, mirror rocks, even mirror stars that shine with mirror light. But because mirror photons do not interact with our eyes or our instruments, all of that light would be utterly invisible to us. A mirror star could be blazing away and we would see only darkness. Its light would pass through your roof, your body, and the entire planet as though none of it were there. The only way these two worlds could ever touch is through gravity, the universal language, the one force that does not care what a thing is made of, only that it has mass. And this connects to a serious mainstream adjacent idea about the dark matter that we already know makes up most of the mass in our galaxy. For a long time we assumed dark matter must be simple, a featureless cloud of ghost particles that does nothing but provide gravity. But in 2013, the physicist Lisa Randall, with Matthew Rees, asked why it had to be so boring. Ordinary matter is not boring. It cools, it clumps, it forms atoms and molecules and planets and people. What if some fraction of dark matter can do the same, shedding energy and collapsing, not into a diffuse cloud, but into a thin dark disk hidden within the plane of our galaxy? They called it double-disk dark matter, and while later measurements of how stars move have pushed back hard against a substantial dark disk, disfavouring the strongest versions, the idea cracked open a profound possibility. If dark matter can cool, it can form structure, and if it can form structure, then who is to say how far that structure goes? Atoms, chemistry. Perhaps, in the wildest extension, something more. That extension has a name, the shadow biosphere, an idea explored by scientists like Paul Davies. And I want to slow all the way down here, because this is the emotional heart of this whole section, and it deserves stillness. Consider what it would mean if a dark or mirror sector could not only form stars and planets, but could cross the same threshold our own matter once crossed, from physics into chemistry, and from chemistry into something that grows and responds and lives. Then there could be, occupying the very same space as the Earth, the very same volume as the room you're in, a shadow world. And because its matter does not interact with our light, it would have no way to push against ours. The reason you do not fall through your floor is that the electrons in your feet repel the electrons in the ground. But a shadow substance has no such repulsion with us. A shadow rock, a shadow tree, a shadow being would have no physical barrier against your body at all. Its atoms would glide between yours, never colliding. It could pass straight through the wall, straight through you, and neither of you would feel a thing through touch. To such a being, you would be the ghost, and to you, it simply would not exist. You could be sharing your living room right now with an entire ecosystem, predators and prey and quiet living things, occupying the exact same coordinates as your couch and your lamp and your own body, tuned to a frequency of reality your senses were never built to receive. Not alone, never alone, and with no way through sight or sound or touch to ever know it. I hope you feel how that idea inverts the oldest fear, the fear of cosmic loneliness, and replaces it with something stranger. Not emptiness, but a crowded room you cannot see into. But touch is not the only sense, and gravity, again, is the exception to every rule. Mirror or shadow matter would be invisible and intangible, yes, but mass is mass, and mass bends space, and gravity you can feel. If a shadow object were dense enough and passed close enough, you would not see it block the light, but you would feel its weight. And this gives a genuinely unsettling physical framing to an experience that millions of people have had, one you may have had yourself. In sleep paralysis, a person wakes but cannot move, and reports, again and again across every culture on Earth, the same three things: a presence in the room, a feeling of being watched, and a heavy weight pressing down on the chest. Let me take you into that room, gently, because I know for some of you this is not abstract at all. You surface out of sleep into the dark, and you know at once that something is wrong, because your body will not answer you. You try to lift a hand and nothing happens. You try to call out and no sound comes. And into that helplessness arrives a certainty, primitive and total, that you are not alone, that something is in the room with you, close. And then the weight settles onto your chest, a pressure that presses the breath out of you, and you cannot turn to look, and you cannot move, and you can only wait. Now, to a neurologist, this is well understood, and I want you to hold on to that, because it is the truth and it is a comfort. During dream sleep, your brain paralyzes your body, so you do not act out your dreams, and in sleep paralysis you simply wake while that paralysis and a piece of the dreaming brain are still switched on. The presence, the weight, the fear are your own mind, caught between two states. That is the real explanation, and it is enough. But the physicist chasing the dark sector cannot help but notice that a felt weight, a pressure with no visible source, a mass you cannot see but can somehow feel, is exactly what a gravitational encounter with something invisible would be. If a being of mirror matter lay down in the space where you were sleeping, its atoms would pass harmlessly through your ribs, but its mass would not pass through the laws of gravity. Its weight would pull gently on the matter of your chest. You would feel the pressure of a thing your eyes could never register. I am not telling you that is what sleep paralysis is. It is not. But I am telling you that the speculative physics and the ancient human experience rhyme in a way that is hard to unhear once you have heard it. And finally, before we leave this idea of an invisible wind of foreign matter, I owe you one real experiment, presented honestly. Deep beneath a mountain in Italy, shielded from cosmic rays by more than 1 kilometre of solid rock, sits a detector called Dharma, and for more than 2 decades it has reported something strange. It sees a signal that rises and falls with the seasons, peaking in the summer and dipping in the winter, exactly the pattern you would expect if the Earth were ploughing through a wind of dark matter particles, moving faster into that wind in June as it swings around the sun, and slower in December as it swings back. Within its own data, the signal is extraordinarily strong, statistically overwhelming. It is the kind of number that in most contexts would be called a discovery. And yet, and this is the crucial honesty, no other experiment has been able to confirm it. Detectors built specifically to check Dharma's claim, using the same material, have not found the matching dark matter signal, and other highly sensitive searches have seen nothing compatible. So Dharma's modulation is real in the sense that the detector really does flash with the seasons. But the interpretation that it is a dark matter, wind blowing through your body millions of times a second, is not accepted, because the rest of the field cannot reproduce it. It is a genuine, unresolved thorn, a maybe that has refused to become a yes or a no for 20 years. So here is where this leaves us, standing in a room that might be far more crowded than it looks. A neighbouring universe perhaps a whisper away, a vacuum that may be quietly pushing worlds together, a mirror sector that could be forming its own silent stars, a shadow biosphere that our loneliness never imagined, and a wind we cannot feel that one buried detector insists is really there. None of it proven, all of it built, brick by brick, on at least one thing that is genuinely true, and every path we have walked tonight has led outward, to the cosmos, to the horizon, to other worlds. But there is one more direction the leak could run, and it is the one that should unsettle you most because it does not point out toward the stars at all. It points inward, toward your own memory, your own choices, and the strange question of whether the you sitting here is really the only one. Part 13. The Leak into You and the Long Way Down. In 1957, a graduate student at Princeton named Hugh Everett looked hard at the central equation of quantum mechanics and noticed something that has haunted physics ever since. Quantum theory describes tiny things not as having definite properties, but as spreading out into a haze of possibilities, a wave of maybes. And the standard story said that when you measure such a thing, the wave collapses, the maybes snap down into a single definite outcome, the spinning coin lands on heads, and the tails possibility simply vanishes. But Everett noticed that the mathematics does not actually contain that collapse. There is no step in the equation where the wave chooses. The equation just keeps evolving smoothly, forever. So Everett made a radical proposal. What if the collapse never happens? What if, when you measure the coin, the universe itself splits, branching into two equally real versions, one where the coin is heads and one where it is tails, and a version of you goes with each. Both of you fully real, both of you certain you are the only one. This is the many worlds interpretation, and I want to be clear that it is not a fringe idea. It is a legitimate, if minority, way that serious physicists read quantum mechanics. In this picture, reality is not a single thread but an endlessly branching tree, splitting again and again, trillions of times a second, every time a particle could have gone one way or another. Which means, if it is true, that there are countless versions of you, branching off from this very moment. In one branch you're still listening. In another you drifted to sleep a paragraph ago. In another you got up for a glass of water. These are not, in this reading, mere hypotheticals. They are physically real worlds, as real as this one, containing versions of you as awake and certain as you feel right now. The only reason you cannot see them is that the branches have separated, decohered, fallen out of step with one another so completely that they no longer interact, or almost never interact. Because there is a real experimental technique called weak measurement, developed by the physicist Yakir Aharonov and colleagues, that lets us touch a quantum system so gently that we barely disturb it, catching sight of its behaviour before it fully settles. And in the most dramatic tellings, this is where the branches are said to brush against each other, where a particle in our world might feel the faintest push from its own ghost in a neighbouring branch. I have to be careful and honest here, because this is a place where the popular story stretches the science past its limits. Weak measurement is real, and quantum interference between possibilities is real. But the claim that alternate timelines exert a force on ours, that the version of you who made a different choice is physically nudging your neurons right now, goes well beyond what the physics supports. It is a poetic extrapolation, not an established result. Hold the wonder, but do not let anyone sell you the ghost as a fact. Which brings us to the internet's favourite version of this idea, the Mandela effect. The strange phenomenon where large groups of people vividly and confidently remember things that never happened, or happened differently than the record shows. Whole communities are certain a famous name was spelled one way when it was always spelled another, certain of lines from films that were never spoken. And a popular theory holds that these are not mistakes at all, but memories bleeding through from a slightly different timeline, evidence of realities merging and overwriting one another. It is a seductive idea, and I understand its pull completely. But here I have to be firm because this is exactly the kind of place this channel refuses to mislead you. There is no scientific evidence that the Mandela effect is anything other than the ordinary, well-documented fallibility of human memory. Our memories are not recordings. They are reconstructions, rebuilt each time we recall them, easily reshaped by suggestion, by expectation, by the confident agreement of other people who misremember the same way. Collective false memory is a thoroughly studied psychological phenomenon, and it fully explains what we see. The multiverse overwrite is a lovely story. The science says it is your own beautiful, unreliable brain. And no, before anyone asks, a particle collider did not rewrite your childhood. The energies involved are dwarfed every day by cosmic rays hitting the atmosphere, and no experiment we have run has any power to edit memory or history. I say this plainly because respecting you means correcting the record, not flattering the myth. And yet the many worlds picture carries one implication so personal, so quietly disturbing, that it has unsettled physicists since it was first named. It is a thought experiment often called quantum immortality, and its logic is simple and cold. Consciousness requires a working brain. You can never experience being dead because there is no you left to have the experience. From your own first-person perspective, then, the only branches you can ever find yourself in are the ones where you survived. In every branch where a car crash or an illness or an accident ends you, that version of your experience simply stops, the screen goes dark, and there is no one there to notice. But in whatever branch you happen to live through, however improbable, you are still there, still experiencing, and from the inside it feels as though you simply got lucky. Follow that all the way to its unsettling end, and it suggests that the observer behind your eyes might never experience its own death, only an increasingly improbable, increasingly strange continuation, always finding itself, against all odds, in the one thin branch where it survived. I want to be equally clear that this is a philosophical thought experiment, not a testable claim, and most physicists regard it as a curiosity rather than a prediction about how you should live. You cannot act on it, you cannot verify it, and it should not change a single decision you make. But it does something to you to hear it. It makes you glance back at the near misses in your own life, the accident that missed by an inch, the illness you should not have walked away from, and wonder, just for a second, which branch you're really standing in. Let us come back up, out of the mind and into the cosmos one final time, because there is a long-term stakes to all of this that we have not yet faced. In 2001, the physicists Paul Steinhardt and Neil Turok proposed a model that took away our beginning. For a century we have told the story of a single Big Bang, one miraculous moment when everything burst out of a point of infinite density and time itself began. But Steinhardt and Turok looked at the mathematics of brains and realized that a Big Bang looks suspiciously like a collision. They developed what is called the ekpyrotic model, from a Greek word for conflagration, and in it our universe is a brain, and a neighbouring brain drifts in the bulk parallel to us. Every so often, across almost unimaginable spans of time, the two brains drift together and touch, and the moment they touch, the energy of that gentle cosmic collision floods both brains with heat and light and matter. To anyone living inside the brain, that moment would look exactly like a Big Bang. In this picture, the Big Bang was not the beginning of everything. It was the most recent clap of thunder in an eternal storm, one collision in a cycle of collisions stretching back forever and forward forever, universes touching and parting and touching again. This is a serious minority theory, not the consensus, and I want that on the record. But it reframes something we can actually measure, and the reframing is chilling. In the late 1990s, we discovered that the expansion of the universe is not slowing down as gravity should demand. It is speeding up. Galaxies are flying apart from each other faster with every passing age, driven by something we named dark energy, simply because we had no idea what it was. In the standard picture, dark energy is a property of empty space, a constant push woven into the vacuum. But in the ekpyrotic picture, that acceleration is not a push at all. It is a pull. It is the gravitational attraction between our brain and the neighbouring one, growing stronger as the two draw closer, exactly the way two magnets accelerate toward each other as the gap narrows. If that reading were right, then the accelerating expansion we observe would be the smoking gun of an approaching collision, a measure of how close the next Big Bang really is. I do not think most cosmologists believe this, but I think it is worth knowing that the number we casually call dark energy has, in at least one serious model, been read as the sound of a wall coming closer, and there is a faster way for physics to end us, one that does not require any neighbours at all, only the ground we already stand on. It comes from the stability of the vacuum itself. In quantum physics, the vacuum is not nothing. It is the lowest energy state a field can settle into, and the unsettling question is whether our vacuum is truly the lowest, or only a temporary resting place. Picture a ball in a valley. If it sits at the true bottom, a nudge just rolls it back, it is stable. But if it sits in a shallow dip partway up a mountain, it looks stable, it stays put for ages, and yet a hard enough kick could send it over the lip to crash down to a far lower valley below. In 2012, at the Large Hadron Collider, we finally measured the mass of the Higgs boson, the particle tied to how the vacuum gives mass to everything else, and its value came out at about 125 giga-electron-volts. And that specific number places our universe, as best we can calculate, right at the knife's edge between a stable vacuum and a merely metastable one, the ball possibly resting in the shallow dip rather than the true valley. If our vacuum is metastable, then somewhere, someday, a quantum fluctuation could nudge a tiny bubble of the true, lower vacuum into existence, and that bubble would expand outward at nearly the speed of light, and inside it the constants of nature would be rewritten so that atoms as we know them could not exist. Let me be very clear before anyone loses sleep. Even in the metastable case, the expected time for this to happen is astronomically long, vastly longer than the current age of the universe. The danger to you, tonight, is for all practical purposes zero. This is a statement about the deep far future and the fragility of the rules, not a threat hanging over your evening. But the idea has a haunting feature worth sitting with for just a moment, because it ties every thread of this night together. Imagine you are sitting exactly where you are, holding a cup of coffee, thinking about nothing in particular, and imagine that somewhere out in the dark a bubble of new physics has been expanding toward you at the speed of light for 1 billion years. Here is the terrible elegance of it. Nothing can travel faster than that bubble, not light, not radio, not any warning of any kind. The news of the end can only arrive at the exact same instant as the end itself. You would be looking up at a patch of sky that appears perfectly ordinary, stars shining as they always have, the light from those stars reaching your eyes at the very same moment the wall of new physics reached your face. There would be no flash to see, no sound to hear, no interval to be afraid in. 1 nanosecond you're lifting the cup, worrying about tomorrow, and the next there is simply no cup, no you, no worry, the continuity of your experience snipped like a film strip. You would never even know. And there is a strange mercy folded into that, if you look at it the right way, which we will in just a moment. There are finally 2 whispers from the edge that I promised you, and they belong here at the close. The first is real. In 2006, a NASA balloon experiment called Arcade lifted a radio antenna to the top of the atmosphere to listen to the faint hiss of the early universe, and it heard something it could not explain, a radio glow far brighter than the sum of all known sources, a roar where a whisper was expected. Scientists subtracted every galaxy, every known object, and the excess remained. It is called the space roar, and it is a genuine, unresolved anomaly to this day, though the leading explanations are mundane, likely a population of faint early galaxies we have not fully counted, not the friction of colliding universes. The second whisper is the hum, a low-frequency droning sound reported by a small number of people in scattered places around the world, Taos, Bristol, Windsor. A rumble felt more in the bones than heard in the ears, with no agreed source. And I will tell you honestly that the mainstream explanations for the hum are entirely of this world, industrial noise, infrasound, quirks of human hearing, and that there is no established link whatsoever between it and cosmology. The idea that it is the creak of our brain under the pressure of an approaching wall is pure speculation, offered as the kind of thought that arrives at the far end of a night like this one, and clearly labelled as such. So now, at the very end, let me answer the question I posed to you at the very beginning, the one I promised I would not dodge. Is another reality leaking into ours? Here is the honest payoff, and it is not a tidy yes. The mathematics of our best theories genuinely leaves the door open. Extra dimensions may be real, gravity may leak, walls may be porous, and a handful of genuine anomalies, the cold spot, the space roar, the larger scale flows, really do rattle that door in a way no one has fully explained. And at the same time, every single rung of tonight's ladder has an ordinary explanation waiting beside it that requires no other universe at all, and in several places the dark flow, the mirror wind, the bleeding memories, the best current evidence leans against the dramatic story. That is the true state of things. Not a sealed box we can prove, and not an open wall we can prove, but a boundary we cannot yet see clearly, standing at the edge of what anyone knows. And do you remember the image from early tonight? The dice on the table, and the idea that someone reached in and turned them over. I want to gently turn that image over one last time, because maybe no hand reached in at all. Maybe we were never singled out, never targeted, never struck. Maybe the truth is stranger and kinder than that. Maybe the table itself is simply far larger than we ever imagined, and we are one small game among countless others, and the odd rolls we keep noticing are just what it looks like to sit at the edge of something immense. We are not the centre of the story being reached into. We are a tiny, temporary pattern near the rim of something we will never see the whole of, and that, I think, is where the fear is supposed to turn into something else. Because if you cannot stop the brains from drifting together, and you cannot steer the galaxy out of the current, and you cannot patch the vacuum or close the wall, then a peculiar and wonderful freedom falls out of the mathematics. All of it, every collision and every leak and every long, slow slide toward whatever is at the bottom, is so far beyond your reach that it quietly cancels the weight of everything small. The embarrassment you're still carrying from years ago, the worry about the message you have not answered, the sense that you are behind, that you're not enough, that you're running out of time. Set it against a universe that may be one membrane pressed against an ocean of others, and it does not shrink into nothing out of cruelty. It shrinks into perspective. It gives you permission to loosen your grip. We are, when you get right down to it, a bit of lucky waking matter that happened to switch on for a brief moment in the middle of something enormous. We got to see the stars. We got to feel the warmth of a nearby star on our skin. We got to lie awake and ask why, which as far as we can tell is a rare and astonishing thing for a pattern of atoms to do. We are walking a narrow path over a drop we cannot fathom, yes, but the view from the path is the most beautiful thing there will ever be. So here is where I want to leave you tonight, with the wall between realities still standing, thin and porous and unexplained, and with the current still carrying us all somewhere we cannot name. None of that is in your hands, but this is. Right now, in this improbably stable moment, in a universe that may be pressed against 1,000 others you can never see, your atoms are holding together long enough for you to feel something. That is not a small thing. That may be the only thing. The universe may be cracked, and the boundary may be leaking, and the dice may have been turned by no one at all, and you are still here, still breathing, still listening, still, against every impossible odd, yourself. Rest easy. The wall has held this long, and you are still here,